If, like me, you accidentally found yourself on the internet and discovered discussions between various Go generics opinion havers, then you may also have been overwhelmed with the bloodbath that ensued and the pure hatred thrust upon Go for society. Well, I'm pleased to report that the dust seems to have settled on that now, and people have calmed down a bit. So I figured now would be a good time for me to make some clickbait on generics now that nobody gives a shit. I'm going to basically be doing a code review of a package in the Benthos stream processor where we're using generics now, so we can see how we're using it, why we're using it, and hopefully nobody's going to get their feelings hurt. This package also makes use of the sync.Cond package, which I think is actually more interesting than generics are. It's also quite a niche feature that you might not want to use all the time, but when you do use it, it's very powerful. So it is worth knowing about. So hopefully we can have a bit of fun here. It doesn't all have to be bleak. Okay, so we're going to be looking at this package called checkpoint, and there are two implementations of a checkpointer. There is uncapped and there is a capped. We're going to be looking at the uncapped first because the capped is just an uncapped wrapped with a cap, okay? So it's less interesting. This is actually not a lot of code. This is less than 90 lines, and it's basically just one thing. So we've got at the top here a struct type called uncapped, and that has a generic type parameter t, which can be anything. Ignore these two fields for now. What we have at the bottom here is these two fields start and end, and these are both a struct defined at the bottom here called node, which is also generic. This is also of type t, and that has a payload which is of our type t, and then we have this previous and next pointers that each node has, which points to other nodes. So a lot of you are going to be looking at that probably and thinking, gee, that looks like a linked list. And congratulations, this is a linked list. You're correct. It's a linked list where we keep references to both ends of the list. And the rest of this implementation is just doing linked listy things, but in a very specific way and with a very specific purpose. So it's not going to be very easy to understand what this is doing without understanding the problem that it's supposed to be solving. So as quickly as I can, I'm just going to cover that before we carry on with the code. Now, Benthos is a stream processor. Don't freak out if you don't know what that means. It reads a continuous stream of discrete message payloads from one or more sources of data over a network. And the sources can be arranged in different protocols and broker types. The important thing is that they all have roughly the same functionality, which is called an acknowledgement system. So when you're reading data over the network, in order to guarantee that you get everything you're supposed to and that there's no sort of data loss, even when things get a bit spooky and weird, rather than just reading the message and forgetting about it, what you do is when you're done with the data that you've consumed, you give back what's called an acknowledgement, and that's sort of a receipt that says you're finished with that message now. If you don't send that, the thing that gave you the data in the first place is responsible for sending it again, over and over and over again, giving you duplicate after duplicate until you have acknowledged that you've seen it. And that's the only way we can guarantee you see everything you're supposed to. Otherwise, there might be data loss. So that's delivery guarantees. It's very important for everybody, basically, who cares about their data. Benthos takes it super seriously because there are lots of edge cases in the world of stream processing where things get flaky and people don't have the delivery guarantees that they think they're getting because they haven't covered themselves for certain things. Benthos aims to solve all of those problems. I have other videos on that stuff if you're interested in, but in this particular problem, we're solving one specific issue. Now, some queue systems make it really easy to distribute messages across horizontally scaled services and parallel processing threads because the messages can be consumed in any order and they can be acknowledged in any order. So you're acknowledging the specific message and it doesn't really interact with others. Some queue systems aren't like that. So Kafka is the big one. Kafka works differently because it's a log of data rather than individual messages. And what that means is you're reading a sequence of messages in a specific order. And when you acknowledge messages, instead of just acknowledging the individual messages, you actually save a position on that log so that the next time your service starts up after a crash or a restart or whatever, it picks back up from where it left off. We call that committing an offset. So an offset in the log, you commit it, which is you're saving it, and that's basically an acknowledgement. If you want to get parallelism from consuming that data, but you're consuming it sequentially, you have the option of having multiple logs. So you can just distribute messages across multiple logs, and each parallel processing thread or horizontally scaled service gets a subset of those logs. Those are called partitions in Kafka. And that's great, but it's a bit naff because you have to kind of preempt how many partitions you're going to need. And it might change over time that you have more parallel processing threads required or more horizontally scaled services, whatever. Basically, people don't like that. So what often happens instead is people will just consume any number of logs and process the messages they consumed out of order. Who cares, right? You've read the data, you can do whatever you want with it. So if you want to read a sequence of messages but process them all asynchronously, that's fine, you can do that. A lot of frameworks, libraries, and things that abstract around Kafka will just allow you to do this, and it's fine in theory, but it's also very dangerous. The danger is if you just consume messages asynchronously and whenever they're finished with, you effectively acknowledge them by committing their offset. You might be acknowledging messages and committing an offset that comes after messages that are still being processed and you're not finished with. The important thing is it's impossible to acknowledge a message in a log-based system without acknowledging all prior messages. So if you do that naively, then you might be susceptible to data loss the next time your service restarts or crashes or whatever. When it recovers the connection, it's going to continue where it's saved, which comes after messages that it didn't finish with, so you've lost that data. Lots of frameworks and libraries will allow you to process messages asynchronously, and you can just acknowledge them whenever, and they will handle all the offset commits and stuff like that for you. And they don't communicate the fact that you're susceptible to data loss, and that's either because they don't understand the problem and they haven't anticipated that, or they just don't have good documentation that clearly outlines you might lose data if you process these messages out of order. And it's on you to make sure that you acknowledge them in the correct sequence. In Benthos, we need a solution for this where we don't need to trust that users understand this issue. We understand it for them, and we make sure that we've got strong delivery guarantees, even in cases where they do want to process messages out of order. And that's what the checkpointer is for. Now, in order to solve this problem, the checkpointer needs to keep track of every single message that has been consumed from a specific log. And while it's being processed, it keeps a reference to that message in its offset. As messages are processed asynchronously and they're finished with, when each message gets finished with, we inform this component that, hey, this particular offset is now done, we're finished with it, we never need to see it again. And then what it will do is, based on that information, at any given moment in time, it will be able to tell you what is the highest possible offset on this log that you can commit without it being after messages that are still being processed. So basically, we're going to call that a checkpoint. What is the highest viable checkpoint that won't result potentially in data loss? Now, that solves the data loss problem. We'll never lose a message as long as we respect that. But it introduces a new problem, which is if you arbitrarily allow messages that you've consumed to block the committing of offsets that come after it, either because it's stuck in some sort of retry loop for a period of time, or maybe it just takes ages to process, there's no limit to how much data you can consume after that point that doesn't get saved. And then you imagine like one message is blocking for ages, you read a whole load of messages that came after it, you can't save any new positions because this one thing is blocking, and then the service restarts or it crashed and came back online. The next time it starts back up again, it's going to reread all of that data and you're going to get a load of duplicates. Some people don't care about that so much. Some people do care about it a lot. The important thing is we will have some configurable maximum gap between the current highest viable checkpoint that we're actually able to save and where we currently are reading from the log, so that gap doesn't reach a certain size. And it might be that the size has to be really small because we definitely don't want any duplicates, or maybe it's going to be quite large. But when it gets reached, we want to apply back pressure by blocking consumption of new data until that gap either shrinks naturally because it's automatically recovered, or somebody comes and intervenes and fixes the problem and restarts the service. So there's two problems there. The first one is keeping track of all the offsets and keeping track of the highest viable checkpoint we can commit. And the second problem is once the gap reaches a certain point, then we block for as much time as it takes for it to recover. Okay, so back to this uncapped implementation. So I told you to ignore these two fields at the beginning. I would like you to de-ignore them now, and we can acknowledge their existence. So the two pieces of information, other than the actual linked list itself, is a checkpoint, which is a pointer to type T. So this represents the current highest checkpoint we're able to commit. And it's a pointer because there might not be one yet. If we're just starting up and we've only consumed a few messages and nothing has been acknowledged yet, there might not be a checkpoint. And checkpoint position is information that we're going to use for working out the logical gap in messages between the current highest checkpoint and the last item that we've added to the list. So these are two pieces of information that we have to keep because it's not going to be part of the list itself. I'll explain that in a second. So let's revisit our track method. So this has both the payload, which is our offset. We know that's our offset now. And that can be any generic type. And in Kafka, it's going to be an integer, but don't worry about that for now. And then we've also got batch size. So the reason why we keep track of a batch size is because we can't rely on the offset itself for working out the gap in messages from one offset to another, because you can have compaction, for example. So that's not a reliable indicator. And we also can't, so in Benthos, you don't have to process messages one by one. What you can do is you can optionally batch messages up as you're consuming them. So in windows of say like a second or a discrete number of messages, and then you can process that as one logical unit. And the important thing here is that when it's done like that, they all get acknowledged at the same time because it's one logical thing that gets processed as a whole transaction. In which case, it doesn't really make sense to track each specific message's offset because they're all going to get acknowledged at the same time. So what we do instead is we just track the biggest offset of that batch, and then in order to calculate the gap in messages, which is the more useful way of expressing a cap, you want to be able to express that in raw messages and not have to think about the batching mechanism or anything like that. So in order to work out the number of messages between one offset and another, we have to include the batch size when we're tracking all of this stuff. And what we start off with is a new node to add to our linked list that has the payload, which is the offset, and then it's got a position. Now, the position is ever incrementing. As you add more and more items to be tracked, they all have a position that's larger than the one that came before it. So we're basically counting from the first thing that gets added to our list and just keeping it up. Hopefully, we'll never have an integer overflow, but who knows what will happen? The whole thing will explode. But we're not worrying about that for now. So the position starts off as just the batch size, but we'll adjust that in a minute. If we don't have a start to our existing list, then this is the first thing being added to the list. So it could be that this is the first thing ever being tracked, or it could just be that we've emptied the list and then we've added something after that. Either way, the start now becomes our new node that we've just created, and its position will be the batch size. If there is an end, so the list is populated, then what we do is we take the reference to that end and we retain it in our new node. So it has a pointer to the thing that came before it. And then we increment the position of the thing that's being tracked with the position of the latest item on the list, the last item on the list, and then we swap the two. So the way that we do that is we give a reference to the end of this new one, so they both have a link to each other. So we can traverse the list in theory in either direction. And then the end will always become the new thing that's been pushed on top. So effectively, we're kind of pushing this thing away. So we lose a reference to it, but then the new node that's been pushed on has a reference to it. That's how linked lists work, generally. If there isn't an end, and this is the only thing being added to our list, and it's the only thing that's going to be there, then we increment the position by the checkpoint position. So that means if we empty the list and then we start contracting again, we don't lose reference to the fact that the checkpoint is of a certain point in terms of messages versus the thing being added on, so we don't lose that count anywhere. And then finally, we return this closure function. So this removes the thing that we've just added from the list. So you track an offset, you get back a closure, and the closure that comes back is responsible for removing the offset that you've tracked from that list, which is effectively our acknowledgement. We're basically signaling that we're happy for this thing to disappear. We're done with this data now forever. So we can commit its offset safely and not worry about it. in order to do that, what we do is we remove that item from the list. And if there is something before it, what's really important is we cannot acknowledge that message because there's something that came earlier. And if we were to acknowledge it, that thing would then lose its delivery guarantees. So what we do instead is when we move an item from the list and there's something that came before it, the thing that came before it gets its offset and position. And the reason for that is we always want the highest possible offset that we can commit. And therefore, if we remove an item from the chain and something came before it, and we want to retain the fact that this higher offset existed, but now it's safe to commit, we essentially collapse that into the thing that came before it, so that that information isn't lost. So basically, we're just removing an item from the chain, and then the item before it becomes the previous item in the chain. If that's not the case, so this is the earliest thing in the list and it has been removed, that's when we can update our highest possible offset, because we've just removed the earliest thing, which means nothing came before it that is still in flight. And that's the critical part of this code base. So what we can do in this particular instance is we can populate our checkpoint and checkpoint position fields. And because checkpoint is a pointer, we have to pull that out into a variable and then take an address of that. And then finally, the beginning of our list, so the earliest item in the list, because we don't have one anymore, we just removed the existing one, it becomes the next item in our chain as far as this node is concerned. It might be nil, in which case we've emptied the list, but who cares at this point? Now, if there is a next in the chain, we give it the reference to the previous thing in the chain, which could be nil if this was the first item. What we're doing here is we're basically just making sure that when we remove something in the middle of the chain, the two broken links are now connected, so we don't break the list. And finally, if there isn't a next item in the chain, then the last item in the end, so this end reference, the last item in the chain, becomes the one that was previous to us. And again, if that happens to be nil, then who cares? We're just basically making the field nil. Finally, we return the current highest checkpoint, and that's a convenience thing. It means that a component can be reading messages, tracking the offsets, and then in some of the Go routine, potentially it could be committing a particular offset by first acknowledging the message with this component by calling this closure function. And then what happens afterwards, it wants to know what the highest checkpoint is that it can then actually send over the network and commit as an offset. So to save us having to make two calls, it makes sense to just return it. Even if it hasn't changed, we just return the highest value that you can commit, and then you can just make sure you mark that anytime you call this function. The highest method, this one's self-explanatory, we just return the highest checkpoint. It's useful to have this as a separate method just in case. It's for when we're shutting down. So you imagine we're doing a graceful termination and we want to do a final commit with the absolute highest offset. It's easier to just call this and then keep that information outside of this component. And then finally, we've got this pending method. So pending is responsible for actually giving you the logical gap between the highest offset that we've committed and the latest offset that we've tracked. And that calculation is fairly straightforward. So if there is no end, there's nothing in flight right now, we can just return 0. But if there is something in flight, then we take the position of the last element in our list, the last thing, which is the biggest position we've got, and then we just negate the current highest checkpoint offset. So basically, you imagine like the gap is just moving along a counter. So as the position gets bigger, so does the checkpoint position, and they just keep chasing each other. And there are times when they match, and there are times when they're bigger. And that's pretty much it. That's this whole component. So we have the gap implementation, but you may have noticed that we don't have any mechanism by which we could possibly block. Now let's just quickly stop there and have a bit of a chit chat. Let's have a bit of a healthy dialogue between you and me. You might be having a bit of a whimper. Oh, why is he using generics there? Oh, so let's address that, shall we? Does this thing need to be generic? It obviously didn't start off generic. This was originally made way before generics were an option. But even then, it didn't need to be generic at all because it was just for Kafka. And Kafka has offsets that are integer-based, and therefore they will sit nicely as an integer in memory, and therefore you can have a struct with an integer in it instead of a generic type T. It was also not a linked list. It was just a slice because I was doing a bit of integer arithmetic rather than having to maintain a linked list as a bit of a shortcut. It wasn't as easy to reason about, but it was neater in terms of like memory use, I guess. But that had to change because of AWS. So I wanted to build a connector for AWS Kinesis, which is very, very shockingly similar to Kafka, except one of the differences is that offsets are not nice integers that you can fit in a 64-bit integer type. I think it's even 32 in Kafka. They are actually just an arbitrary string, which is numerical, but it's too large to fit in a 64-bit int, as far as I remember. But even if it could, it's kind of arbitrary. It doesn't really mean anything. As far as the documentation lets me be aware of, there's no real shortcuts there. So you can't translate the string into an integer type and do arithmetic or anything like that. It's just a string you have to keep track of. So it suddenly became an arbitrary payload. Now, I'm not opposed to duplication. I'm not opposed to copy pasting something that I had for Kafka if it fit in the Kinesis world and reusing that. I'm also not opposed to implementing something new and just having an integer one and a string one that works for both. However, this isn't a large amount of code either, so it definitely is a good candidate for a bit of a copy-paste jobby. But it's also really important code. So like I said, the use case for this particular piece of code is to prevent data loss, which is very, very important. So even though it's only a very, very small piece of code, I don't want to have it duplicated because it's a potential weakest link in the service itself. So if there's any bugs in here, ideally we need to preempt that. We need to find it with tests and some deep thought, some deep philosophical thought. And I don't want to have to repeat that effort in multiple places and make sure that they both have parity with each other, because this is really important stuff. I would rather have an implementation that's maybe a teeny bit less efficient than have it duplicated and maybe forget about one or the other. So what I ended up doing is when Kinesis came about and I needed to have the same implementation for that, I changed my integer-based solution. I just made it generic by having boxed and unboxed values to the empty interface type, and that was fine. That was 100% fine. It still wasn't a linked list at this point because I was kind of lazy. I just left it. I didn't have the integer arithmetic shortcuts, but I still kept it in like a slice thing. And then a contributor, shout out Grayson, came along and turned it into a linked list, which was more appropriate at the time, but we still had this empty interface type. And again, I felt like that was fine because any component that was instantiating a checkpointer was the only thing that was going to be interacting with it. So it's not as if something was instantiating a checkpointer and then boxing certain value types and then passing it to some other component that might have other assumptions about what the checkpointer contains within it, where, the boxing and unboxing process might be a bit risky. It wasn't that. It was just a single piece of code was instantiating a checkpointer and using it and getting rid of it. So it seemed a bit low risk to be having the empty interface and a bit of type conversion back and forth. But then generics came along. Why the heck not? This is obviously a good candidate for it. It's a collection type, which is supposed to hold payloads of different types. So if there's any use case for generics, then this is obviously one of them. It wasn't about performance. It wasn't necessarily about code tidiness or correctness or anything like that. I was perfectly happy with the previous implementation with the boxing and unboxing, but I think generics is a good fit, so why not? Come and get me. This uncapped variant doesn't solve the ultimate problem of our gap, which is we need to block. So let's have a look at maybe the capped variant has something to offer there. Look, I think it does solve that problem. Whoa! So what we've got here in our capped implementation is basically the same thing. We've just got the struct with its generic type parameter t. And then as you can see, we own within this an uncapped checkpointer. And we're mostly just going to be punching through into that. And we have a capacity, so maximum capacity for our gap, saved as an integer. And then we've got this sync.Cond type. So a sync.Cond is basically a wrapper around a mutex with some extra features on top, which we'll go into in a minute. When you instantiate a new capped, it's very, very simple. You just create a new uncapped and keep the capacity, nothing really else going on there. You can call this highest method, and what it does is it uses the lock that we have within our sync.Cond type in order to make, so all this entire component is Go routine safe. So you can use this across any number of Go routines. You can be tracking from multiple, and you can be acknowledging from multiple, and they won't interact. And that's the other responsibility of this, not just enforcing the gap and applying back pressure, but also locking the ultimate checkpointer implementation. So we use our lock, and then we return the punched through highest value that we get from the thing that we're wrapping. And that's very self-explanatory. And then all we have left is this track method, which for what it's doing is actually just basically wrapping the underlying track implementation. So we still call that here, but we've just added some extra stuff on top. So let's just walk through that stuff bit by bit. The signature has also changed a little bit. So instead of just having payload and batch size, we also provide a context, and that's so that this doesn't block forever. We have some sort of way of cancelling the request, and we also now potentially return an error, not just a closure function. We might fail if the context gets cancelled before we're able to yield the resource. Now, the first thing I'm going to tell you to do is just ignore this block here. Let's just hide that for now. That's specifically to do with the context cancellation bit, which is a bit finicky. The important thing is, when we enter this track method, the first thing we do is we lock the mutex that's owned by the sync condition type that we have. That means that there's only one thing working actively here at a time. And then we find out what the current pending number of messages is between the highest checkpoint that we currently have and the last message that got tracked. And if that's plus the current batch size that we're about to track is larger than our cap, we need to block until that's no longer the case. So that's where we enter this for loop. And this could be a busy loop where we just spin around over and over again, keep checking pending, and then wait until something has changed. Maybe the gap has gotten smaller, or the context got cancelled. That would look like, just delete all this. That would look like that, and we would have to we'd have to add a sleep, because otherwise this is going to kill your CPUs, because it's just going to spin around and starve all the other Go routines. So we don't want that. What we need to have is some way of stopping the loop until either something has changed or just waiting arbitrarily. Waiting arbitrarily is bad because it's going to add weird performance issues. Ideally, you never want to sleep, especially somewhere that might be a hot path. So that's not on the table. But luckily, we have this sync.Cond type. So what this does is you call wait, and under the hood, it will unlock the mutex. So other Go routines that are waiting on it can do their own thing. And then it will wait until some other Go routine has called cond.broadcast. And that's a method that will essentially wake up anything that's currently blocked on a wait. So it's a broadcast signal, very similar to if you close a channel and you have a bunch of other Go routines waiting on that channel. When you close it, they will all wake up because the channel's been closed, so they'll get that signal. So that's one way of broadcasting, but it's very difficult to refresh that. So you imagine you might want to have multiple broadcasts or different Go routines waiting for broadcast until something happens. If you need to refresh that, if you wanted to use channels, you'd have to constantly create a new channel and then somehow inject that into the thing that's causing the broadcasts, and you're going to have mutexes there anyway, and it gets really fiddly. Sync.Cond basically encapsulates something very similar in a way that you don't have to worry about. So we call wait here, and that will block this Go routine until something has called broadcast. So where's broadcast in this file? Luckily, it's not a big file, so we can find that somewhere. And it's within this closure that we return. So the signature of this track is very similar to the uncapped variant, where the closure that we give back is the thing you're supposed to call in order to remove the offset you're tracking from being tracked. So the way that this starts off is we get the closure that's returned by the underlying uncapped variance track. So this would just remove it and not do anything else. And what we do is we wrap that with a closure that we return from this method itself, where we add in a broadcast signal. So we lock the resource first. That's optional, I think. In fact, we'll see in the comments here. Broadcast wakes all go routines waiting on C. It is allowed but not required for the caller to hold a lock during the call. So we lock this, but that's actually optional. You don't need to do that. Actually, no, we do need to do that because we call the underlying resolve function. That's what's there. Okay, so what we do is we lock the underlying mutex, so nothing else is going to be actively doing anything within this checkpointer while we hold that. Then we call the closure function that got originally returned from track. That will remove it from the list, and then it's done. So the new checkpoint has been updated if that's appropriate. It's definitely been removed from the list and all that other stuff has happened like before. Then we call broadcast. And what that's going to do is it will wake up any go routines that are stuck here in a loop. So if we've called track from just one go routine, it'll wake up that one go routine. But potentially there might be multiple go routines waiting to track and offset that could all be blocked on cond.wait. And then we obviously return heist because that's what we're interested in when we read the result of the closure function. And then what will happen is this defer will unlock the lock. So what happens is once this gets unlocked, the thing that was waiting becomes unblocked, then gets its own lock on the mutex. So at the end of this call, once it's unblocked, you know you own the lock again. It makes sure to do that before the go routine becomes unblocked. So at this point and onwards, we now have exclusive rights to interact with the underlying checkpointer. What that means in practice is only one go routine will wake at a time. So they all get the broadcast signal and they all will wake up, but only one of them will have a lock at a time. So only one will be active at a time. So you imagine like if you've got 10 go routines that are all blocked on this cond.wait and you do a broadcast signal, they will all wake up, but one after the other. Until this one yields the lock, the others will stay asleep. And then what we do is we just recheck pending. So we re-obtain the current pending number of messages from the underlying thing, and then we see if we're going to re-enter this loop or not. If pending is small enough, we won't. But if it's still too large for us to proceed, then we call wait again. And at that point, we will yield the lock for other go routines to wake up, and we will block until another broadcast signal has happened. So we would need this closure function to get called again by something else. And because that's the only way that the gap is going to change, it makes sense to block until that's actually been called. If that's not the case, and the pending now is small enough to fit within our cap, we call track, and then we return our closure function, and it's only after the return that this defer unlocks the lock, which means if there's another go routine that's also stuck in this loop, by the time it wakes up and does another pending check, we've already added the batch size of the previous one, so we still take that into account, and it means that we don't have a race condition where multiple go routines could potentially add their thing and then increase the gap more than we would expect. Because they're all locked, it means we'll be calculating it independently for every single go routine that wakes up. And that's that. So like I said, if we could have used a channel here, we could have used some sort of implementation that has a broadcast channel for whenever this function gets called, we close the channel, and then maybe we would call some function that makes a new channel, which would then have to be acquired every time something wants to wait on that broadcast signal. It'll need to reacquire the latest channel, but it's a lot to maintain. It's probably subject to all kinds of race conditions, difficult to test, and it's just not worth it. Sync.Cond does this job perfectly, and the only circumstance where this can go badly for you is if you haven't anticipated enough broadcasts to unblock you wherever you're waiting. So if you haven't anticipated every single place where a condition might change that the go routines that are waiting are interested in, there's a chance for deadlocks where they will just never wake up again, even though things have moved onwards. But as long as you always make sure that anything that changes the conditions by which something would be waiting has a broadcast somewhere, you'll be fine, even if you have a lock. And then the final thing, so that's basically that. This would work. You could deploy this right now, and it would do exactly what you want. It's going to block until there's enough capacity, and then and then allow you to track your offsets, and it still maintains the highest viable checkpoint and all that stuff. However, it's kind of naff that you wouldn't be able to cancel this, because that means during shutdown and things like that, where you want to gracefully terminate and you give up essentially on processing a particular message. You just want to forget about it and reconsume it the next time you start back up again. Well, you no longer care about this method, and therefore it doesn't really make sense to keep it blocked. That's where this bit comes in. So we provide a context to this method, and what we want is, if that context gets cancelled, we abandon the attempt to wait until the gap's reduced. And as far as I'm aware, the only way, so I think they've added some context-based methods to some of the stuff within sync. As of the time you're watching this, maybe there will be stuff in sync.Cond as well. However, at the time of making this video, there's nothing, so we have to implement this ourselves. And it's not complicated, it's quite straightforward. What we do is we could ignore that. Let's pretend that doesn't exist. What we do is we wait until context.done unblocks. So basically the context has been cancelled. And then what we do is we call cond.broadcast, and that will unblock any go routines that are currently waiting on the condition. And what they'll do is before checking the gap and whether or not it's now small enough, what they do first is they just check whether there's an error on the context. And if there is, we return that. Because that indicates that the context has been cancelled for whatever reason. And that would solve this particular problem. However, if the context that's provided doesn't have a cancellation on it already, then this go routine would block forever, and we would leak go routines. So even though track would unblock eventually when the gap gets small enough, if you're providing it a context that doesn't ever cancel, then you would just keep spawning a go routine for every single call to track. And that's what this other bit is for. We basically enforce there will always be a cancel, and therefore we don't leak these go routines. So we create a new context from the one that's been provided, which also has another cancel function if there's already one. And then what we do is we spawn this go routine that will block on context being done, and we'll provide a broadcast, but that will be forced even if this method has resolved. So imagine we've returned our closure function and we've managed to track an offset. If we then exit this function, this defer gets called, the context gets cancelled, and then we'll do this broadcast, and the go routine will end. It'll finish. And this broadcast here is harmless. It doesn't hurt us necessarily to wake all the go routines that might be blocked on this gap, because all they're going to do is they're just going to re-enter the loop. So it's cheap to do something like this, and obviously go routines themselves are quite cheap. So I don't anticipate this is a real issue, but obviously it would look a lot neater if we could just if this was encapsulated within the condition itself. But I can also understand why they might not want to do something like that, because context is quite a high level package, whereas sync is quite low level. So yeah, I can understand why it is as it is. So hopefully that was fun to watch. Hopefully I made a solid case for why we chose to use generics in that particular case, and hopefully you're not deeply hurt by it. If you are, then feel free to leave a comment, and maybe that will prompt some sort of emotional response in me as well. The sync.Cond stuff I think is really interesting. If you didn't know about it and you feel like giving it a try, I will just say be very careful. It is pretty easy to introduce deadlocks. But other than that, it's awesome. I use it in a few places, and it's similar with generics. It's got a specific use case, and I don't just use it all over. But when I do use it, I'm very thankful that it exists. Like this video and subscribe to the channel, or things are going to happen that are out of my control.